Logic for Computer Science, Classical and Non-Classical, Springer, 2019, Chapter 10. Chapter 10 is about predicate automated proof systems and completeness for classical predicate logic. We will prove the completeness theorem for a QRS proof system, which is extension and generalization of our RS system for propositional logic. So part 1, I will present the QRS system. Part 2, proof of the completeness theorem. And the second, part 3, is about Skolemization and clauses and how you get. So this is like a little bit introduction, not little bit, introduction to the resolution, which we are not covering in detail. So QRS system, we define and discuss Rashowa-Sikorski-Gentzen style proof system. Q, because it's for predicate logic. Before, RS was for propositional logic, and propositional version was in chapter 6. These both proof systems admit constructive proof of completeness theorem, and you will see the constructive proof of the QRS system is more sophisticated version of RS system. That's why we covered propositional system before. So we adopt Rashowa-Sikorski 1961 technique of construction a contra model determined by decomposition tree for QRS system, and this is generalization of our propositional RS system. The other Gentzen type predicate proof system included original Gentzen system LK and Li for classical and intuitionistic predicate logics are obtained from the propositional versions, which we covered in chapter 6 by adding, enriching the language and so on, of course, but adding quantifier rules. And it can be done in a similar way as we do for, we generalize propositional RS to predicate QRS. I love the sentence. We leave this generalization as an exercise for the readers, for students. We also leave as an exercise the predicate language version of Gentzen proof of cut elimination theorem Hauptsatz, which we did in chapter 6. And also there are more other types of automated theorem proving system, but based not only, we cover Gentzen sequence and we cover RS systems, but there are more and different automated proof systems, which we talk already a lot about resolution. There is a natural deduction mentioned by Gentzen in his Hauptsatz paper in 1935, but was developed by Doug Pravitz in 1965 and is called now Gentzen-Pravitz natural deduction. A lot of logic books and a lot of logicians and computer scientists like more natural deduction. We don't cover everything. So there's also some very important systems which are called semantic tableau deduction methods invented by Everett Beth in 1955, and which was simplified and beautifully developed by Raymond Smulian in 1968, and now it is called Smulian semantics tableau. And also there's a resolution. The resolution method can be traced back to Davids and Putnam papers in 1960, and the work as a whole is called Davis-Putnam method. And it was quite difficult and not, it was just the beginning. And methods were all difficulties and over complication were eliminated by Robinson in '65, and he consequently developed it into what we call Robinson resolution, or just we call it resolution. Resolution proof systems for propositional or predicate logic operates on clauses as a basic expressions I already mentioned many times. We defined here and proof correctness as effective procedure of converting any formula of predicate classical language into the corresponding set of clauses for both propositional and predicate cases. So here, let's define the QRS system. We do it fast because it's just generalization of the system you already know. So the language is a full flat language of predicate language. So where we have language, these are connectives, and these are predicate, functional, and constant symbols, and that's how we write the language. And expressions now are finite sequences of formulas, as we did before, and we denote as before by gamma delta. And system, so these are our basic sequences, finite sequences of formulas. And rules now, we have two rules of inference go into two groups. One is, first group is propositional connectives, and they're exactly the rules we know perfectly well relative to the richer language. And second group deals with quantifiers, and you have universal quantifier, existential quantifier, negation, like everything, negation of conjunction, negation of universal, negation of disjunction, negation of implication, negation. So the schema of the rules are the same. Now, logical axioms is any sequence of formulas which contain formula and negation, and we wrote it, but now it's not literals. It is any sequence of formulas, so it's a little bit more general. And now we have a formal system, all those rules, and we are going to write those rules. Now, we need a little bit to bring back the language. Atomic, what are literals? Literal, this is because this is resolution language and we use it. Atomic formula or negation of atomic formula is literal. So now we say literal is set of A with A is atomic or negation of atomic formulas in propositional where variable negation of variable, and you have the same positive literals and negative literals. And notation is the same. Gamma prime is like in our system are finite sequences of literals, right here. Finite sequences of literals, and you have rules. You have disjunctions, they're exactly the same rules, but the formulas are different, like in RS. So group 1 is exactly the same. And you have group 2, you have universal quantifiers. And now it is, you have to be very careful. Of course, the rule says if you have a y, I can deduce for all x, ix, and these are just the Morgan rules. So, but here is important condition that a variable y here in the rule is a free individual variable that does not appear in any formula in the conclusion. It means in any formula in this sequence. So that is called, and that was invented by Gensen, and if not, the rule wouldn't be even sound. So the variable y in this rule is called eigenvariable. We use it German because it's Gensen. And also occurrences on y in AY are fully indicated. And existential quantifier means that if here is the premise, if you have a t, you can deduce there is, where t is any arbitrary term. Now you can here deduce, and also you must have, there is xax, you can deduce, and deduce there is xax. So remember that those rules in our system, as well as it was in propositional case, these are really decomposition rules. For the proof search, we use them as the decomposition rules. So really decomposition rules would go from here to there. So that rule means that if I get rid of that there is xax, I replace this x would be any term, but I want to search which term. I have to repeat this here because eventually you will get to that part, and again you would be searching for the term for which you want to eventually get the axiom. So, and again, in all those rules, I remind you that they are very exactly the same. Gamma prime on the left side is always sequence of literals, as we did in all propositional connectives rules. So when you build the decomposition tree, you know that you have to go from left to right to find first decomposable formula, as we did in the case of in case of propositional logic. And the formal proof is formal proof, but we will use the tree proofs, right? So that is exactly the same definition of a tree proof relatively to different language as we did in propositional case. I repeat it just not to to make you go to the previous chapter 6. So, for example, this is the same example. You build the proof trees the same way as we did in propositional case. And also the proof, so the main advantage of Gentzen type proof system is that the proof search is deterministic and automatic. We conduct the proof search treating, as we did before, treating the rules as the decomposition rules, right? So we treat the rules as decomposition rules. So I am not repeating all the setup we already had in chapter 6. And decomposition 3 is exactly the same. We have the sequence is on the top of the root. And if delta is decomposable, or an axiom, indecomposable, it means sequence of literals, delta becomes a leaf, and then you do the same if it's decomposable. Then what we do, as we did before, we traverse delta from left to right to identify first decomposable formula B, and the main connective of B, identify the proper rule of inference, and we put its premises on the node below, or its left and right premises if the rule is 2 premises on the left and right nodes below respectively. And we repeat until now the difference is that until we obtain leaves, it means indecomposable or axioms. Axioms now does not have to be indecomposable. So that's what I say, obtain leaves when you have axiom or indecomposable or an infinite branch, because when you look even on our existential quantifier rule, if you go from this is this is indecomposable, that is decomposable formula. You replace, drop the quantifier, you write A, and then you repeat this. So when you keep from left to right decomposing, and then it can give you infinite branch if you don't get an axiom. And I'll give you an example in a second. So that's why the decomposition trees now can be infinite. In propositional case, the decomposition trees were always finite. And also the decomposition tree are okay, so now this is a general how you do. Now let's define the decomposition tree more in detail. Of course, for that part is as we did before, so there's no, we have to look of the decomposition tree in the case of quantifiers rules. That does the Morgan laws, so they act exactly the same as our previous trees. Now we have to see how we decompose universal quantifier and existential quantifier. And that is the whole point. And these are more complicated, right? So now we have the sequences indecomposable literals. You see our universal quantifier, or the other case, you have existential quantifier. And how you define the next step. And we have specific conditions. Now, first, we assume that we put all the terms of the language in 1-1 sequence. So ST is 1-1 sequence of all terms of the language, because variables are terms. So if you want to decompose this, you get rid of this quantifier and you put a variable, which is a term, from the sequence, and that variable needs to fulfill that condition. So this is and in the case of existential quantifier, if you want to decompose this, you put a term. And this is arbitrary term. And then we have, so we have to define which term you choose, which variable you choose, and so on. So that's why to define in detail our decomposition trees, we put all the terms into that ST is a sequence of all terms, and I'm going to write it here because ST is T1, T2, Tn, all terms of our language. And of course, remember that variables are terms, and we use the symbol fat T for terms. So all variables are terms. So the variables sit here, and the terms, we know what they are terms. So this is we assume that we have all this sequence of terms are here. And now, let's gamma be a sequence of the tree in which first indecomposable formula has a universal quantifier. So it means you have gamma prime, first indecomposable formula has for all x. So we write the sequence, we drop quantifier, and we replace that quantifier by a y, where this variable y has to fulfill that condition. And the condition is the variable y is the first free variable in the sequence. So we put y you traverse the sequence, and y is somewhere here, is the first free variable in this sequence of terms which does not appear in any formula here. And that corresponds to the restriction of the variable in the rule. So you always, that's why you traverse also the sequence and you find the first one which does not appear, in this y is the first one which does not appear above. And for the if the first decomposable formula is now universal, so we decompose universal, we put a t as a child. Now, with t fulfills the following condition. T, because I want to keep putting new terms. So the condition for t is that t is the first term in our sequence. So now we put for existential quantifier, we put t sit here, is the first term in our sequence that such that at, because you replace there is x ax by at, so t is the first one such that at does not appear in any sequence on our tree above our gamma prime a t, and of course because you have there is a x. So here you do this and you can replace, you put a t, so above you had gamma prime, there is x, and you have the whole tree above delta a x, delta, there is x a x, that was here. And now you look above the whole tree, which you already constructed, and you choose as this t the first term in the sequence which you haven't used yet. So it says each time when you look, what is there is? There is means that there is a term. So you are sure that you each time look for the next one and next one, a different term that you already produced. So, and of course, the sequence of the terms as t is 1, 1, right? This is 1, 1 sequence. So, and all rules have those gamma primes, right? So you have first decomposable formula to decompose after gamma prime. You go from left to right and you have first, so you have uniqueness. Decomposition, again, decomposition tree guarantees that the decomposition process is also unique in the case of the quantifiers, and of course is unique in all other cases. So that we have uniqueness theorem, which we had for any formula, the decomposition tree is unique. And now we have that if decomposition is finite and O leaves an axiom, then we had found a proof. So A is probable. If is finite and contains an axiomlet, okay, so or T is finite or T is infinite. So the decomposition tree is finite. So, and all leaves are axioms, we found the proof. If T is finite and contains non-axiom leaf, because it's unique, that's bad, or T is infinite, then there is no proof. So your search is unique. So if it's finite and you found non-axiom leaf, you are done. Or it can be infinite, and this infinite is good that it has to be infinite, because the predicate that was Gentzen proof of semi-decidability of first-order logic. Semi-decidability, it means that if A is a tautology, we'll find the proof. But if A is not a tautology, you get infinite search. So you don't have a finite decision. So that's, it has to be. And here is a nice example, which I'm going to explain. You have to go slowly through this. That, okay, let's look at this. We have De Morgan law. I want to prove the De Morgan law. So here you have main connective is implication. So you do the implication rule. This is propositional. Now you have double negation. You do double negation. And now you have for all x, you got for x. So now your main connective is gamma prime is you go from the left to the right. So gamma prime is empty. You have main connective is universal quantifier. So what you do, you apply it. And now you have to write this y. There was a condition on y, remember? If you were choosing y for universal, y was the first free variable formula. And here I wrote you always have to write it down, right? Y x1, this y is x1, first free variable in our sequence. So you call it, you go, and you find first free variable, which we can call it x1, because you might have more, in the sequence, such that the condition for universal is not appear above. So does not appear here. So such that it does not. I can put x1. It might have some variables. I don't know which variables are in the formula, but you have to choose the first variable which does not appear in this sequence. And now, and that is already our literal. We treat A, capital A, as a predicate. So I don't know what A is, so I treat it as literal. So my next step would be the connective would be existential quantifier, and what it says. Now, you choose x1 is the first term, but I want in the sequence such that AX1 does not appear on the tree above. So this is a little bit first term, so you can choose a lot of times, but I won't, because I know that I'm going a little bit faster. I know that I want to have axioms, so I have to put the terms. So I said x1, I put here as x1 first variable, first term in the sequence, such that the formula ax1 does not appear above. And formula negation, you see ax1 appears, but formula negation does not appear anywhere on the tree above, so I can choose that exactly x1 and I get axiom. So And I just prove that it has a proof. Now, another decomposition tree. Here, I look. I have existential quantifier. I put T1 is a first term in the sequence, such that negation does not appear above, because, and now I do again, so, and I treat that is my indecomposable. Now I again apply this to that, and again T is the first term in the sequence such that the condition was AT1 does not appear at AT1. I can put the T1 here because AT1 does not appear on the top. And now let's look at the tree. What is happening when you have just there is XAX? So how the tree would look like, right? I apply, I have my terms here, and there is, I take the first, because there's AT1. This is our conditions, remember. So I wrote all these conditions in red. So we choose first term in the sequence such that AT1 does not appear. I can too, so I can put T1. Now I want to decompose this. And remember the rule asks us to put the quantifier again. The formula, there is XAX at the end. So here I choose T2 such that AT2 does not appear. So I cannot put T1 because T1 is not equal T2. So this is 1-1 sequence. And now you keep going. So here now you have in this stage, you pick up T3 such that T1, T2, T3 is different, and now you just go infinite branch, so the decomposition tree is infinite. So those, when you construct those trees, or you write a program to construct those trees, of course they depend on the way you put your terms in the. So there's another example, which is just to make you aware of the condition. Here I have universal quantifier, right? By the y condition, x1 or y condition, here you choose first variable such that this formula, right? That this is quantifier and here's the formula. So the whole formula does not appear in here. I pick up the first one. Now I do the Morgan law, so that is no condition. And now, I do the Morgan law. So now, oh no, I have here, no, sorry. Here I have negation of conjunction, and I do negation of conjunction. And now I have, so this is indecomposable, this is indecomposable. Now my main connective is conjunction. So I have two branches. And now I have this, and again, here existential, T is a first term. In the sequence, such AT does not appear. But you can see, you can keep going, choosing those terms in the sequence somewhere, but finally, as long as you finally can, because when you can find in this sequence some term which would be exactly that variable x1, and you get an axiom. And you can choose this because AX1 does not appear above. So because your T was each time different. And here you do the same, you have axiom, you found the proof. So what it means that it is possible to choose eventually a term ti equal x1 as the formula ax1 does not appear on the tree above that node. And by definition of the sequence, this variable is placed somewhere in the sequence, so this variable x1 is a certain term, and you finally find will find that term to have an axiom. And there's more examples. I very carefully wrote all the conditions, so when you train I will give you on the test, I will give you just a formula to construct the decomposition tree. So that is how you have to write. You have to write exactly, to be very careful, why you can put a variable, where you can put the term, which term, how you do it. And for example, here, when you do the composition, I wrote a beautiful comment. You see, you have to write all those comments. And here, you finally, on one branch, you get axiom. But on the other branch, you can see you have only there is x, and you would get infinite branch. So, so the proof is not decidable because we look, we say, oh, infinite branch, but computer cannot decide it. So now is the proof of completeness theorem. It's due to Rashowa-Sikorski, and it was one of the biggest results at that time. That's why we do it. And it was the first time ever such proof was invented. Such technique of the proof was. And we did it. That repeats, in a sense, what we did in propositional case. It means I adopted that proof to propositional case to because it's just easier to see how f travels the tree and so on, and how you do it. So now, because we are in predicate logic, we defined a model and a contra model. Just a reminder. What is a model of a predicate logic or predicate language? A structure is a model, and we write it, a structure M is a model of A if for all variable assignments, A has all these variables, structure is a model if and only if MV satisfies A for all variable assignments into the universe of the model, and we denote that the structure is a model of A. And I is called the interpretation, and M is called the universe of the model. And contra model, it means you have to find a structure. We have to find a structure, and you have to find a variable assignment such that it does not satisfy the formula A. And tautology formula is predicate tautology, and denoted tautology A. We also say A is valid in the structure if and only if all structures are models for A. And we extend it for the sequence, that any sequence we write delta gamma, the disjunction of all formulas. The structure is a model for gamma, if and only if is a model for disjunction of all formulas of gamma, and we say that gamma is predicate tautology if and only if that is true in all possible structures. And now is the goal to prove the completeness theorem. Again, I remind you that definition of the strong soundness, the rules of, because our rules, we prove them to be strongly sound. the inference rule is strongly sound if the condition holds for any structure. So M is a model of the set of premises if and only if is a model of conclusion. And we prove that all the proof system QRS is strongly sound. And then you have strong soundness theorem. So now we want to prove the completeness theorem. It means that we prove the completeness part of the theorem, and we want to prove for all completeness part is any tautology that has a proof, and we prove the inverse implication as we did by so it means we want to prove if there is not a proof, then there is not a tautology. So it means we can, the unprovability of a formula allows us to define a contra model. Now, reminder, the tree theorem says that two conditions. The tree, you have tree is finite and contains a leaf which is not axiom. So not probability means that in the case of finite, the tree has non-axiom leaf, or tree is infinite. And we do the construction of contra model in both cases. So first, let's look at particular case, because you can better understand what is the structure and how you construct that contra model in this our case. So let's do the case that tree is finite and contains non-axiom leaf. And before you do general method, let's do this construction for that particular case. But here is any formula. Really, you construct the trees for a particular formula. So let's take the formula A, capital A, is a formula Px and Rxy, that P and R are two atomic formula. P is one argument predicate, and R is two argument predicate. So here I construct the tree, because remember when I was showing you the construction of tree for that, for capital letters, I said that we treat A as if it was one argument atomic formula, because you don't decompose it anymore. So, so now we have a particular formula, and we construct the tree, and we go in normal way, right? This is the Morgan law. Then you have here your connective is universal quantifier, so you are now here, and now negation of disjunction, and we go on the tree, and you construct now. You see, this is literal negation of atomic formula. This is negation of atomic formula. These are atomic formulas. Now you have this. You have all these conditions, so you know what those x's mean. x2, what you can, and here you cannot choose x1 because of the condition. So here you have this. Now you have a conjunction, and you have non-axiom leaf, and you have non-axiom leaf. You have even two non-axiom leaves. One is enough. So tree is finite, and these are sequence of indecomposable formulas, sequence of literals, because these are atomic, and atomic formulas, or negation of atomic formula. So we choose one leaf because it's enough. We are strongly, the system is strongly sound. So it means if I put the leaf into F, it means I found the contra model for the leaf. F would go up the tree to the formula. So that was our F or contra model walking up the tree to the formula because of the strong soundness of the rules. So now I choose one leaf, for example, this one. And we use that non-axiom leaf to define a structure, which would be a contra model, and assignment V such that MV does not satisfy A. And next thing, which is, so to define the structure, we have a structure is, I'm going to write the structure M is universe interpretation, right? So I have to define what is universe, and then V is from, I'll bring it later. So now we have to say what is M. The universe M is the set of all terms. Good set, it's very nice, infinite. Good, so we put M equal the set of all terms, and we have to define interpretation. And we say that Q is a predicate symbol, an argument predicate. So I say an argument predicate, T of interpretation key. And I say that Q1 interpretation, we say that this is true for terms if and only if, and remember, we have A, not A, B in propositional case, and we wanted that to be false. It means that we had to put all literals into F. So if a variable or formula appear with negation, we would put it to, so here you will put A equal, so B, sorry, and C and D, right? A will put F, and here if B appeared with negation, we would put B equal true. So that was our, how we did it in propositional case. Now those propositional variables are, the propositional variables are atomic formula. So we say that atomic formula holds or is true for those terms if and only if negation of Q T1 Tn appears, you see, if negation of B was on the leaf, so if this is on the leaf, we put that, if negation is, we put that this is true for those terms, because the universe are those terms, and false otherwise. So we put that, you see, A was false if appeared without negation. So here, in this case, we put the negation of the formula appears on the leaf, and we put Q, we interpret QE of that is false, does not hold otherwise. So it's exactly the same schema as we did before. And for any functional symbols, of course, if you, that is for what happens with Q, and we interpret any functional symbols of T1, Tn is just f of T1, Tn, because interpretation is what this means in the set of terms. So whatever you had means exactly the same. So that was this building the models and contra models of the formulas in the set of terms was one of the biggest ideas of building models for, you don't need the numbers, your terms are at the set, so the terms are a very good set to build models or contra models. So it means that leaf, on this leaf, what we have, this is true for x1, and it's not true for x2, right? Because x2, that you put for false, so you put this is not true, and px1 is true for x1 because negation must be false. And the same for that atomic formula, interpretation of x1 is true, holds for x1 and not for any variable y from the variables. And now you can write it that now we have any variable assignment v, and we put, you see, we have to define the variable assignments into the set of term. What you do, the variable assignment would be identity. So any term would be that what you wrote, what is a term. So if you say v is identity for any variable, of course we have px1 under v would be exactly what you have, right? So t e, this is your structure, under v would be exactly px1 because that satisfies, because x1 is x1, and you know that it px1 was with the negation. You see, px1 was with negation, so px1 must, that v must satisfy px1 and so on. So we show that v in the structure does not satisfy the leaf because it didn't satisfy, it does not, all those formulas are put into the false. And so that is a contra model. So that is exactly the same structure as we did in our construction of the contra model for the, just for the variables, right? With negation put to true, and if A was false, so all leaves were false, so that would be a contra model for all the leaves by the definition of our model. And now we can do it in general method for any formula, which is a little bit more complex, but the idea is the same. You, in general, you take always the structure. There's the universe of the structure. You set that set of all terms, and now you have the language. So you have for any predicate symbol p, an argument. You interpret this as what? Subset of t to the power n. It means is an argument relation, and key q I between t1, tn of elements of t, because this is our universe, holds for the true if and only if negation of the formula q t1 tn appears on the leaf and does not hold otherwise. So you see here, in the propositional case, it is exactly what we did. In propositional case, we had V of x. You have our non-axiom leaf, and we say Vx was, for the x's x, we put Vx was f, where Vx appears on the leaf. So that is our x, and is t if not x appears on the leaf and anything otherwise. So this is the same idea that Q, you interpret, yes, yeah. You say that holds if negation appears. So that means if negation is true and otherwise is false, so if does not appear. So this is exactly the same idea. And then, of course, so this is for any predicate. Now you have to define what's happening for constant. Constant, again, interpretation of constant is a constant. Constant is a term. And the same functional symbol, fi of t1 tn would be ft1 tn. And variables are identities we did for, so this is, and obviously we have that for any structure such defined, the structure V does not satisfy P if P appears on the leaf, does not satisfy F if it appears on the leaf, the structure satisfies T if negation appears on the leaf, and that is our contra model, strongly sound system. That structure, now structure, the whole structure satisfaction travels on the top, and we have a contra model for the formula by the strong soundness formula. Now, the next case, which is a little bit more complex. So that is a nice case because it's exactly, you can see it. But now, when the tree is infinite, it means we construct, if tree is infinite, it means like I gave you this example. This is, let's look at this example, right? We have the example and you have, we construct the infinite branch. And so the branch would be, look like this. And that would be general case. So now the branch looks like this, and now those t's which you put is one sequence of our all terms. And what you do on this infinite branch, what you do, you say that PIT holds if negation is on the branch, and does not hold is negation of the branch. So you repeat the same pattern as we did on this infinite branch. And of course, constant is constant, and f is f, so everything is exactly what is written, because and you get that we got by structure walking, by strong soundness walking up the tree, we get a contra model. And general method, we have let's A be any formula which does not have a proof. And let T A be infinite decomposition tree. And we want now to construct a contra model on infinite decomposition tree. So we have infinite branch, right? We have infinite branch of the T written from top in the order of appearances of the sequences. So infinite branch is gamma 0, whatever. This is our infinite branch on the tree. And we want to construct now a contra model on that infinite branch. But we have to look which are in decomposable formula. So formulas on that infinite branch. So let's form a set LF, leaves F, because they are like leaves or in decomposable formulas appearing in at least one of the sequences on the branch. So LF is the set of formulas such that gamma is in a certain BA, gamma is in BA such that B appears in gamma I. And we have that if I is less than I prime, and in the decomposable formula appears in gamma I, then also appears, keeps going by the definition of the branch. And since none of them are axion, for every atomic formula, at most one of the formulas, P or not P, is on that set. And that is the key of contramodel definition, right? So, and we do now exactly what we did. For any predicate symbol, we interpret Qi, T1, Tn does not hold. It means negation. For terms, if and only if is on the branch, does not hold. False, if is on the leaves, now is on the branch. And does hold if negation is on the branch. Otherwise. So, and then we have directly from the definition that M is a contramodel for M, and then we do the proof of it by induction. And you can see you define the order of the formula. Order is the number of connectives, and you have different. So and then you construct. We construct the proof by contradiction. Assume that it's a model. So if it's a model, you will go through the whole branch by the order. You will see that you will get the contradiction because of the way we define the order of that formulas on MF. And then we show that it cannot be a form of any of our normal formulas. It cannot be of the form of there is x bx, and so it means always in each case we get a contradiction, and we have the proof of completeness theorem. So completeness theorem, of course, it seems very complex, but when you look back at chapter 9 for the proof of Hilbert-Steig completeness theorem, which also uses the same set of universe of terms as we did here. So that is a very easy proof. Okay, now the last part is Skolemization and set of clauses, which is also very important. It's a part of resolution, AI, and so on. So at least I want to, okay, in Prolog, each Prolog program, you don't need to do Skolemization because it has Skolemization built in. So you can just put into Prolog program all these quantifiers, and it would do exactly what I'm going to explain you what it is. And then finally, whatever you give would construct the set of clauses. So what I'm showing you now is what it is and how that part of Skolemization, which is works. So the whole process, we want to, okay, resolution-based proof system operates on a set of clauses and uses resolution rules as the only rule of inference. So the first goal is to define effective procedure for any formula for predicate language, a set of clauses, CA, which are logically equivalent with the formula A, and prove that logical equivalence. And that process of transformation, we convert a formula of the predicate language into an open formula of the language, and we call this language L star. by process of elimination of quantifiers from original language. And that elimination method of quantifiers is due to Skolem 1920 and is called Skolemization of the language. So first you have a Skolemization, and we have a Skolem theorem, which we nicely prove, that a resulting formula through this process A star is equisatisfiable with A. So it means, this is a nice word, equisatisfiable. It means it is satisfiable if and only if the original formula is satisfiable. It's a little bit complex because you will see that the language L star is a richer language than L. So we add some things to the language. So also the satisfaction is a little bit. So this is, but it is logically equivalent. It's equisatisfiable. And the stage S1 is performed as the first step of resolution-based automated theorem prover. So now we want to define a system QRS star based of the Skolemized language. So I first show you the nice procedure, which is easy, and then I will show you how to construct that Skolemized language L star. So now we are already in this Skolemized language L star, and we define the proof system in that language, which does not have quantifiers but have other things. And we use it to automatically transform a formula A star of that Skolem language into logically equivalent set of clauses. And the final system the final result of the stages, 2 stages, is the set of clauses of Skolemized language L star called clausal form of original formula of the language L. So the transformation process for any propositional formula A into logically equivalent clauses is directly from RS. So we use directly our IRS system. So let's now L be propositional predicate. And now we call literal is atomic or negation of atomic formula. We denote LT the set of literals. The clause is a finite set of literals. So this is definition of the clause. And that language is, we know what's predicate, atomic, and negation is called literals. It's exactly the same definition. An empty clause is denoted, this is called empty clause. And now, so this is a clause, a finite set of literals. We denote by C a finite set of clauses. So fat C is C1, Cn, finite set of clauses. And the clause is a finite set of literals. And okay, given a propositional predicate language, the sequence gamma is the finite set of LT star determined by gamma is a set of form out of all elements of sequence gamma. So this is just that gamma is a sequence, and now I said C gamma is a set made out of sequence. That's what it means. So for example, if you have, what it means, if you have a sequence and C gamma would be the set made out of the sequence. Because sequence you can repeat I, so the set C gamma would be the set made out of this. So the same for predicate, if that is a sequence of literals in predicate, and this is another set of literals of sequence, but the sets out of this is exactly the same because you cross the repetition. So that was just to have a good notation. And then in any clause, for any clause we write that delta C is a disjunction of all literals in the clause. And M is a structure for predicate language or truth assignment of a propositional language. We have that M is a model for a clause if and only if F is a model of disjunction of elements in the clause. So in the clause, comma is like in a res, disjunction. M is called a model for the set of clauses. And now M is a model for a set C of clauses. M is a model of C if and only if M is model of each clause from the clause. So this is normal because it's a set of clauses. And we say that formula is equivalent to the set of clauses if and only, so which we write like this: A is equivalent to the set of clauses. Formula, set of clauses, if and only if A is equivalent of conjunction of all formulas delta C for all the clauses from the set of clauses. And you have the formula clauses equivalences. For any formula of propositional language, there's effective procedure of generating a corresponding set of clauses such that A is logically equivalent of set of clauses. What you do? First, you construct for the formula, we construct like chapter 6, decomposition tree. We form clauses out of leaves of the tree. And it means for every leaf, we create a clause determined by that leaf. And the set of clauses is L is the set of leaf, CL, where the leaf is the leaf of T. And directly from the strong soundness, we have that A is logically equivalent to that set, and that is the proof. And here you have a nice decomposition tree. You have our decomposition tree. And so the formula has leaves 1 and 2. Set of clauses determined by those leaves is set of, and you make out of sequences sets. So set of clauses is what you take the set, so double A is crossed. And by formula equivalency, you have that A is logically equivalent to CA. It means inside of clause, this comma is disjunction. So that would be A or B or C, and in the set of clauses, comma between the clauses is conjunction. So semantically, A is logically equivalent to that formula. And you can do the same for the predicate logic once you are in the Skolem language. And what you do exactly repeat the same, the set of clauses, everything is in, you construct the tree using QRS star based on quantifiers free language, which is like our normal propositional rules. And you do the same, the set of clauses would be the set of all sets that you have for all leaves of the tree. You have the causal formula from the Skolem language of our quantifier-free Skolem language, because you have only our propositional rules. And this is Skolemization is really how you get quantifiers out of the language. So there's a lot of laws of quantifiers, how you pull out quantifiers in front of the formula. So, for example, I gave you examples how you pull the quantifiers, how you change variables. There are different laws which you can, you have replacement theorem, you have all these nice laws of quantifiers which you can name variables apart. You can, finally, you can pull out all the quantifiers in front of the formula. And this is called Prinex normal form. So any formula of the form when all quantifiers are in front, where this quantifier is universal or existential, it means it's universal and existential, and inside you don't have quantifiers at all. So that is a Prinex normal form. And you have Prinex normal form theorem that there is effective procedure of transforming any formula, classical, into a formula B of Prinex normal form. And you do all these equational laws of quantifiers, which we were playing with long time ago, and you have different ways you name variables apart. You pull out quantifiers using those equational laws of quantifiers, and you finally go rename variables apart, and you just can get at the end a formula which has all quantifiers in front. And I give you example how you get, of course this is the Prinex normal form formula is not unique, and then is a general procedure. So one is example and there is a general procedure of Skolemization. So we show that any formula already in Prinex normal form can be transformed into certain open formula A star. And that formula A star belongs to a richer language than initial language. And that is called Skolemization of the language. So this transformation adds new constant to the original language. They are called Skolem constant. And also process adds new function called Skolem function. And the whole transformation is called Skolemization. So such built extension of the initial language is called Skolem extension and is denoted L star. And we have a procedure. And this is called Skolem procedure of elimination of quantifiers. And the procedure transforms P and F formula into logically equivalent formula to the original one. Example. And so first, if you have open formula, you always build first a closure of the formula. It means closure of the formula is put, here's a free variable, and here's free variable, you have three variables, you put the universal quantifier in front of the whole formula. And then, given a closed formula, so we assume that this closed formula, it means there's no free variables here, these are all variables in B, and all variables are bounded by certain quantifier. We have different cases depending, first, easy case, all are universal. A star would be just drop universal quantifiers. And now, the other case is that all quantifiers are existential. We replace that by open formula where we C1, Cn are new individual constant added to original language. So we add to original language constants which correspond to each quantifier. There is x, is x1 is c1. There is x2 is c2. So this, we add a new constant to the original language, which are not already in our original language. And now the mixed. And now the mix you have, depends how they are. First can be universal, or first can be existential. And if it's universal, we replace by, you just drop universal. So with the first is universal, you just replace A by, first is universal, you replace by x1, you don't change anything. Universal, we eliminate universal. If first is existential, is the same easy, that we existential, we replace existential by a new symbol added to the language. And now is what happens that when you, so we eliminated first quantifier. Now again, you have two cases. And if first is universal, we replaced by, and we eliminate as we did before. But when the first is existential, now x1 is a free variable. You see, now x1 is, this x1 is a free variable in this. So x1 is a free variable in the formula, in this formula. x1 is free variable. So we replace this x1 by a2, where you add, I want to explain, we want to eliminate x2, and I have a free variable. So that second variable, which I want to eliminate, x2, depends now of the x1. So we add a new argument, functional symbol, to the language, and now this x2 depends by, is a function of the x1. And that's how you eliminate this x2. So you add functional symbols. And you keep going. So you add constant or functional symbols depending how many free variables are before. And here is a nice example. And you prove that everything is semantically correct, that Skolem extension of the language is language where all quantifiers were eliminated by added respective Skolem function and Skolem functions. Here's our language. By the Skolemization, we add to F Skolem functions and to C Skolem constant. And you go step by step. And here's a nice example when you look and what you go one by one, very pleasantly. A lot of variables, you have to go step by step, and finally we get a star. You can see by this elimination, depending on the quantifiers, like for example, here you have, there is a 5 here, 5. And I already eliminated the previous quantifier existent, dependent already on those two variables. So 5 would depend, if I want to eliminate y5, I need to add a function. 5 is now the new argument added to the language, which is a function I want to eliminate. It depends on those two variables, 2 and 3, you see? So 5, I need a function which would depend on the previous variables. So, and 6 was universal, so you just leave it and the finite formula would be this. So that is Skolemization. Once we do the Skolemization, we use our RQS rules or our RQS program, and we get the set of clauses for a given formula. You go through Skolemization, and then you construct the tree, like propositional tree, and you have the set of clauses equivalent to a formula. Thank you very much.